Our next speaker is my old university friend, so it's a particular pleasure for me to introduce him. Lasha Ephremidze, you can see the title, so Lasha, for yours.
Yeah. Thank you very much for organizers for inviting me. And this is title of my talk. And I have been participating on this conference 5 years ago as well. And in some sense, I would like to report about the progress, what we have done since this period, during this period. So this was the title of my talk 5 years ago. I have presented numerical method of spectral factorization. And let me briefly explain that spectral factorization this is a special case of general Wiener-Hopf factorization, when matrix which should be factorized is positive definite almost everywhere on the unit circle. And in this case, there is no partial indices. Factorization is canonical, and these analytic and anti-analytic factors of matrix are related, that they are Hermitian conjugate of each other. So, relatively easy case, but of course, numerical solution of this problem is still rather difficult and demanding, and many prominent mathematicians have been working on this problem, including Norbert Wiener. And I presented a new method, relatively new method of such factorization at that time, which nowadays is called Janashia-Laguilava method. And I briefly, in few words, I will describe this method. I will remind you that first step is the factorization, lower upper triangular factorization of this given matrix, where diagonal entries are spectral factors of scalar functions, and we assume that scalar functions can be relatively easily factorized, even numerically. And then we have off-analytic terms, off-diagonal terms, which are not analytic, and we construct effectively unitary matrix which makes this triangular matrix analytic, and this is spectral factor here. And basic computational procedure is this theorem that when we have such matrix, such special matrix, that this is coincides with identity matrix, and last row consists of these entries where this is analytic and these are anti-analytic functions, then we construct also numerically and effectively such unitary matrix, special structure that all entries are analytic and last row is anti-analytic and determinant is 0, which makes this product analytic. And numerical computation of and construction of this metric is basic computational procedure in this algorithm, and plays important role, and I will mention several times during my talk such kind of matrices again. And I remember 5 years ago, I was when I presented this algorithm, I was a little bit disappointed that I was a single person who was working on this narrowed part, because all other presenters were about general Wiener-Hopf factorization. And I was trying, I stayed here for 1 month, and of course working conditions were excellent, and I tried, started to generalize this method, and I tried to use it for general Wiener-Hopf factorization. And in some sense, during this month, I was successful that eventually we produced this first paper where this method in some sense was generalized for general Wiener-Hopf factorization. And furthermore, we have done this for 2x2 matrices, and this Janashia-Laguilava method was for any matrices, and I suggested Gennady that we can. And there was discussions how to attract also during the last conference, how to attract some funds, and I suggested Gennady and insisted to apply for a grant, and I convinced him, and he of course then added many other ideas, and we applied for the grant which we got, this European funding, this big grant, which we still have, and we enjoy having this grant nowadays. What was the mathematical content of this paper? Let me briefly explain that if you have 2x2 matrix, and if you assume that diagonal entries are factorizable, then determinant is also factorizable. Actually, we always assume that in scalar case, Wiener-Hopf factorization is solvable. You don't pay much attention how to do this. And then this matrix can be represented in this form. It can be easily checked that if, say, this 1 entry is factorizable in this way and determinant is factorizable in this way, of course, these are not partial indexes yet. These are just scalar indexes of these scalar functions. Then matrix can be factorized. Again, this is not partial indexes of this matrix. But then these diagonal entries are also, this is analytic and this is anti-analytic, and we still deal with these bad entries here. And we approximate them by Fourier series. And then we, in this approximation, this matrix is already factorized explicitly. And I can say that I have used almost all known facts which was dispersed in different papers related with Lasha method, and only remaining thing was to factorize, it was reduced to factorization of such simple matrix. Here we have these simple entries, and this is polynomial of order m-1. And Ilya, who is a well-known expert in this field, told me that this is well-known how to factorize such matrices. And then and the theorem was ready, and this explicit factorization presented in this paper was ready. Furthermore, I will explain later also, but I was not so much familiar with the difficulties, with the old difficulties existing with computation of partial indexes, and we formulated conjecture that partial indexes of this matrix should converge to partial indexes of the original matrix, which we approximate. And this magic which unitary matrices play in the Lasha method made me to think about this conjecture that this might be true, although not many colleagues whom I shared this my idea were not so inclined to believe this conjecture. Anyway, Gennady was ready to believe, and he, when we met last time during our, in the framework of this conference, he suggested me to at least numerically test this conjecture. And I started, this was most, everything was used known theorems, but this was Chebytarev's algorithm was used here, and I was reconsidering this theorem, and I was able to construct new algorithm of construction for factorization, for construction of Wiener-Hopf factorization of such matrices. Let us, from the beginning, mention some difficulties. Although this matrix looks very simple, but this example shows that partial indexes might not be m and 0 here. There might be any for this is factorization. And we see that partial indexes might be every number between 0 and m here, actually, any pair of numbers. And for small epsilon also, we might have that factorization, these factors blow up. So if epsilon is very small, this might be very large. And we not only produce new algorithm for such factorization, but also we came to conclusion that it might be some kind of new ideas about factorization itself, and I think Gennady will discuss also this, what we are going to mention. And this algorithm was rather simple, and we spent some time to investigating whether it is new or not, and we asked well-known experts in this area if it is new, and they confirmed that algorithm is new. And I will, most contribution will be description of this algorithm. This was, everything was just introduction, and I would like to emphasize the simplicity of this algorithm, and I will try to be understandable for all of you, this algorithm. So these are some properties of this algorithm that we do this step by step, and during this procedure we control the growth of factors, and also we came to this idea that we can make this difference between exact and natural pair of partial indexes and factorizations, which I will explain in details on numerical examples. Okay, now let's start discussing this algorithm. So first step, we just introduce identity matrices, and we call this first step, and this is 1. So determinants are t to power m of this matrix and 1 of this matrix, and this is identity matrix. And this will be at an intermediate stage. We will have such factorization. So these are not. This is analytic. This is anti-analytic, but still is not Wiener-Hopf factorization because the determinant might have 0. Namely, determinant this might not be 0, so this might have 0 at point 0. And what should we do in this case when we are at this intermediate stage? That we consider this matrix at 0. So we consider this matrix, and of course, if any column of this is 0, of course we do know what to do. We just cancel out these zeros outside, and we will divide by this t. It depends whether it is first column or second column. In both cases, we can reduce the zeros of determinants of this function by 1. And then next factor will be either this or this, and this partial index, so-called partial index, will be added either here or here. This is simple step. And if we don't have, if both of columns are different from 0 column, then of course these vectors are linearly dependent because determinant is 0 and determinant has 0 at 0. It means that they are dependent, and both of this equation holds. So alpha and beta both are different from 0 in this equation because these vectors are dependent. And what can we do? That this simple observation that both of these vectors, when we multiply this this matrix at 0 by v, one of the column becomes 0. One of the column becomes 0. And these two simple equations can be easily checked. And in both cases, depending whether m1 is more or m2 is more, this is constant matrix, both of them are constant matrix, and we can move them on the right side, keeping this anti-analytic. So we can always make this difference, one of these difference, depending whether m1 is more or m2 is more, anti-analytic. And so we use, in this case, we will use this matrix, and in this case, we will use this matrix, and we will finally arrive to next step of factorization. This will be next g plus n1 with index n plus 1, and this will be n plus 1 also J minus. And this will be next at next stage, and we will reduce the determinant 1 by 1, and eventually we will derive that determinant will be 1, and factorization will be finished. So let me finalize what happens. That we have this intermediate stage here where determinant is t to power k for some k, and we have two options that either one of the column is 0, and then we use this step, and if none of columns is 0, then we use something similar this, and we came to next stage, and determinant will be same, but one of the columns of this will be 0 after this step. And the factorization will be finished when we reduce this determinant to 1. And we will arrive to partial indices. And what I have said here, actually, it was realized later when we tried to construct algorithm for such factorization, that it was not necessarily such factorization. For any matrix which satisfies this condition, that determinant, polynomial matrix with this property that determinant is just monom of this type, can be applied directly this method. And such matrices played important role in the paper which I showed in the beginning. And so I tried to use this algorithm, same algorithm, to that method. First of all, I will mention these properties of the algorithm, that it works. Oh, what happened?
cable.
Oh, sorry. Yes, properties of the algorithm, which I would like to mention, that algorithm is exact. If we perform all the operations which I mentioned exactly, then algorithm produce exact factorization with exact partial indexes. But of course, it's difficult. It depends whether some numbers are 0 or not. And when we have some round of errors, of course, this is never guaranteed. So it might happen that even small round of errors produce wrong flow in the wrong direction in the flow of algorithm. And therefore, on the other hand, we might control the growth of spectra of factors in the sense that if it is, for example, too small, alpha is too small, and therefore this too large, we can assume that this is too small because of round of errors. We can assume that this is 0, and we can go to different direction, and we can maybe produce different partial indexes. But on the other hand, these factors will not be too large, and we assume that this is important, and we I did not touch it.
You should have.
Ah. Yes. We should introduce different thresholds. It might different when we should assume that this alpha, which is close to 0 because of round of errors or because of difficulty of the problems. Therefore, first of all, I would like to show that this algorithm works well in some known cases where we know theoretically in advance the exact values of partial indexes. And this also relies on Janacek-Laguilova theorem that if we have such unitary matrix with determinant 1, where these are polynomials of order of degree n, and they are conjugates of these polynomials, and it has determinant 1, and if they have common 0 of order m, maximal order m, these two polynomials, then partial indices of these matrices m and by minus n. And for such algorithms, it satisfies this property that determinant is 1. It works very well. So when we checked this algorithm, it works perfectly even for large m. Large m means that instability of impartial indexes is rather tangible. But anyway, algorithm works perfectly, and I will show the numerical simulations in MATLAB if I have time in the end of my lecture. And then we introduced this concept to make difference between exact and natural factorization. And let me explain this idea that, of course, exact computation of partial indices is a very difficult problem. And this, again, illustrates the situation, why it should be difficult. For example, if this epsilon is very small, immediately exact partial indexes of this are n and n minus n. But on the other hand, if we have some numerical procedure and this appears as an intermediate step in factorization, this small epsilon here might appear because of round of errors. And we can neglect it, and we can assume that this is 0, and then we do know that partial indices of not original matrix, but maybe approximate matrix, but we are guaranteed that factors are not large. Therefore, we assume that more natural, we call factorization natural if it happens that we do not factorize exactly matrix. We have to factorize this, but we approximate by some matrix, and we factorize this exactly with factors with reasonable factors. But partial indices of these matrices might be even different. But this exact factorization of these matrices, its factors might be too large, as it is in this example. Therefore, we call natural factorization when we have approximate factorization, but when factors are also bounded and not very large. And why do we what motivates us to introduce this natural factorization, that we assume, and this fact is correct, as was confirmed by Elias Pitkovsky also, although we haven't found this theorem in published form, that if we have the matrix and we approach this matrix with different type of partial indices, so these are not dependent on n, and they are different. And then if both of them are convergent, then it should necessarily, one of these factors should blow up. It should, the norm of this matrix should go to infinity. We formulated this theorem for Wiener algebra, but it should be correct for any norm and for any algebra. And therefore, we introduced this concept of natural factorization when we don't factorize given matrix exactly, especially if this matrix comes from implications. We assume that factors also should come from factors also should be not too large in natural factorization of this matrix. Okay, here I will explain also this conjecture which I which I showed in the paper in the beginning of my talk. So these numerical simulations, these are matrices where we know that indexes are 1 and -1. Simple matrix of first order, we computed from spectral factorization of, so we know that this is outer and this is also without zeros inside from applying spectral factorization of positive definite with this part. And then we take two such matrices and take this middle term and construct such factorization, such product. And we know that this is exact factorization of this artificially. This is construct artificially. And we test our algorithm for approximate factorization of such matrices. And this term S11 and determinant also are factorized in this form, and then we follow the facts which are given in this theorem, paper which I mentioned in the beginning. So we take such factorization first, and then we approximate this positive part. We do not touch positive part, and this is negative part, Fourier index with negative index, and this is Fourier coefficients with positive index. And then we use Janacek-Laguilova theorem to make this analytic. This was main computational procedure in Janacek-Laguilova algorithm. And this becomes positive analytic, and this becomes anti-analytic, and this is remaining matrix which should be factorized. So this has determinant 1, and this also has determinant 1, and this has determinant t to power k. Therefore, we can apply our new algorithm to such situations and actually construct exact spectral factors of these matrices with reasonable factors, which we call natural factorization of this matrix. And numerical computations show that, for example, when we take this approximation n, then these two matrices are rather close from each other, but factorization does not produce correct partial indexes. They show 0, they are correct partial indexes. On the other hand, these factors are blown up. But if we increase n and consider beta approximation here, then we get correct partial indexes 1 and -1. This is a simple example, and the factors also are not blown up. They are rather small here. And I did not have time to have more numerical simulations here, but this is ongoing project and ongoing work. And in every case where something unexpected happens in my numerical simulations and I dwell into situations, I discovered that something important, some good ideas always are generated with this testing these numerical methods. So I think that this project is promising, and we will have final good results eventually for this method. I don't think if you are interested, if I have time maybe for questions, or I can show some results of numerical simulations maybe. I finished my talk.
Okay, do we need to
change file?
No, I have this ready in my computer, but if it's not,
Okay. In that case,
maybe we discuss also questions. But again, this is.
Lasha, what I suggest, while people kind of ask questions, maybe you project that file with the numerical results. Questions?
Do you have a negative result when you have unstable partial indices, but the algorithm doesn't work?
Of course, I have many of such situations, and then I see that they identify reasons why it happens, and positive results, I was able only to select these thresholds carefully. For example, sometimes it should be taken not too large, not too small, and so on. So still, this is ongoing project. If I had computer, I don't know what's the reason. I could show at least some methods where I almost ready to compute computers partial index exactly. But can somebody help me with this?
Yeah.
A button?
Yeah, so maybe press something.
No, this is good, I think. Here I touch something and it stops working.
We are also not getting signal based.
Нет, ну я понимаю просто.
No, I already done, but I want to show this on this screen. What's the reason? It stops sometimes. Oh, yeah, yes, now work, yeah.
Okay. So
That's.
Lasha, you still have like 2 minutes
Yes, I
of your
can.
own time, so go ahead.
Yes, I can. This was for when I knew exactly, because of Janasch-Lagular theorem, I knew exactly the spectral factors, indexes. For example, index here should be 5, and order of polynomial is 10. This unitary matrix I construct with determinant t to power 5, and not always here results are produced correctly, but almost always. Doesn't work here.
Go to editor.
Yes.
On the left. Editor.
Edit.
Yes, I'm not in editor, yeah.
Then,
Thank you. Yeah, correct. In this case, partial indices are produced correctly, or 2 by 2 matrices where I knew in advance this. And we can try again. Sometimes it doesn't produce correct result, and then I have to, yes, computation first time was a little bit slow as it MATLAB does always, but then computations are quite quick, yes. We can increase, for example, we can put here 7, it might not produce, but hopefully it will do. Yes, it is again correct. We can increase also order 15. I think this case, this will not work correctly. Of course, it depends on computations also. Yeah, some kind of error, yes. And when when I investigate in every such case what the reason of error, it gives some new ideas what to do and how to continue these theoretical investigations. Of course, to prove conjecture, probably I realize now how difficult is it, and I'm not so naive as it was 5 years ago, and probably it will be difficult to prove this theoretically if it is even possible at all. But anyway, there is the way to try and to develop some research in this direction. Thank you very much once again for your
Okay, thank you.